Boom. Hello and welcome back to Calculus 3. We are starting chapter 14 talking about vector calculus, which is another calculus in its own. We are going to first talk about vector fields, then we're going to take a look at line integrals, then we're going to take a look at a lot of other cool stuff after that. So, vector fields. The first order of business is to define the vector field in 2 and 3 dimensions, understand what they do, and then move on with the rest. So let's start with the definition of the vector field. So let f and g be defined on region R of R2, right, the 2D. So a vector field in R2 is a function, capital F with the arrow above because it's a vector, that assigns to each point of R a vector fxy, gxy. So we write it as f of xy equals or you can also use the IJ notation if you like that better. Doesn't matter. Whatever makes you smile and happy, because that's what math is all about, especially Calc 3. The next one is the theorem which says that the vector field is continuous and differentiable on R if functions f and g are continuous and differentiable on R. So that's the R region in R square, right? By the way, if you're still confused what is what, when you draw this coordinate system x and y, I hope you understand that this stretches infinitely in all directions forever. It's a flat plane. We think of it as a floor, and then we can bring the dimension z. The entire plane, xy plane, is called R2 because that is the two-dimensional space. So what is R2? R2 is all of the space, and then you are going to have some region R in there. Could be a unit circle, could be a square, could be a triangle, could be half an ellipse, could be inside of the parabola, so could be anything. The idea is that you have the region inside R squared, R2. R2 just means two-dimensional surface, in this case, XY plane. All right, so what are these vector fields doing? So the vector field is going to describe mathematically certain phenomena in physics and engineering and so on. So if you are thinking about, well, 2D is a little bit harder for us to imagine, right? 3D is the one that we go to immediately. So think about wind. No matter where you move in the area where there is wind, you can sense the wind. You can feel the wind at every point. So there is this arrow which forces, well, it's the difference of potentials in air pressure, but we don't care what makes wind. We just care that the air is moving from one point to another. You can get that with a fan. You can get that with the air conditioning. The idea is that the air is moving, and then at every point in space, the air molecule are going in some direction, and that is where that vector points. And then these functions in 3D, you will have FGH, 3 of those. The functions FGH will be giving you in a vector which way the whole thing goes. You can also think about the flow of liquid, so river, let's say, going, you know, the riverbank. Every water molecule is going somewhere. And now you think of these more advanced concepts, right? Like the vector field, gravitational field, magnetic field, electric field, any kind of other particle field. So you have, so these fields are actually just the space that it's all filled with vectors. At any point where there is a particle, there is a vector associated, attached to it to show in which way either the motion is happening or which way the magnetic field points to and goes to. They have few of these graphics to explain that. So if you have whatever this is, a hurricane, you see that there is on the ground, there is a motion that is circular, and then that motion is preserved, but then there is also other motions. So it's very complicated, but vector fields allow us to figure out how that works. And then you have the flow of heat, you have the magnetic field, electric field, and so on. So these are extremely important concepts for your further studies, whether it's electrical engineering or mechanical engineering or whatever other kind of engineering. This is where you focus your efforts, because you need to make airplanes that are aerodynamic. You can't just have a block of thing and just, you know, hey, it's going to fly, maybe. Let's try it. Let's have $1 million prototype, see if it takes off. Oh. So let's take a look at some two-dimensional vector fields. You can actually assign anything and then just figure out what it is when you graph it. And you graph it using the middle school method. Pick a point, compute the vector at that point. Pick another point, compute at that point, and so on. So we can start by and there's no way that you can represent every single point of that field. You know, when you graph x squared, well, you pretty much capture everything that is important, right? You know this is going to go forever and you can't draw forever. Vector field is much trickier in the sense that when you are on xy plane, there's infinitely many points, and try to draw the vector in each single one of them. There's no way in hell, right? So we are going to draw a few vectors to kind of get the idea of the flow of the entire field. So let's see some interesting fields. So let's say field of x and y is given as 0 and x. So I'll just tell you that this is your f and this is your g. And now we say, all right, let's compute at 0, 0. So if the location is 0, 0, that means x is 0, y is 0. When you plug that into the vector field, you get vector 0, 0, which is a 0 vector, which means at the origin, nothing is happening. You decide to try 1, 0. So we're computing a vector now at 1, 0. So x is 1. So we get 0, 1. Well, actually, I can plot that. So at 1, 0, which is here, point 1, 0, I have a vector 0, 1, which is this little guy. All right, let me see what's happening at 2, 0, say. At 2, 0, I'm getting a vector 0, 2, because x is equal to 2. So f component is always 0, and the y component is whatever x gives us. So it seems that that's the one that I get. 3, 0. It's going to be 0, 3. So that one. You can pretty much extrapolate that at 4 is going to be 4 and so on. Well, let's see what do we get if I have, let's say, 1, 1 or 1, 2. Let's say 1, 2. So what's f at 1, 2? Where this is 0 and the other one is 1. So it seems that along over here we're always going to get these vectors that have 1. And then you can try and just say, okay, so what happens for negative 1, 0? And we see we get 0, negative 1. So it appears that on the other side, these little guys go the other way. And as you keep computing, you have all of these vectors that are 2 units long. You have all these vectors that are 3 units long. And so on. So I hope that you see what is happening here. One side pushing up, the other side pushing down. This is shear. Right? This is like a shear motion. So you pick a point anywhere on your x and y plane, and then you compute that in the vector field to see the vector. You draw the vector at that point. Let's see the next one. Vector field is given as 1 minus y squared, 0. And the y is between negative 1 and 1. All right, that sounds good. Let me see what's happening at 0, 0 again. So what's happening at 0, 0? I have a vector field computed at 0, 0. and that's going to be a vector 1, 0. All right. What's going to happen at 1, 0? Well, I don't really have this x anywhere to plug in. So at 1, 0, this is still 1, 0. Because the y is the one that's important. If I plug in 2, 0, I still get 1, 0. So we learned that x component doesn't matter, and that should be clear because there's no x mentioned in your vector field at all. Observe that the last component was always 0. That should be also common sense. So what I'm left to try is what happens if I change y. But look my limits for y. I'm not going to pick any values less than -1 and any values larger than 1. So let me just pick values in between. So how about 0, 1/2? All right, let's check what's happening for 0, 1/2. When I plug that in, I get 3/4 because now y is 1/2, y squared is 1/4. 1 minus 1/4 is 3/4. All right, I'm getting values now. 0, 1/4. If 0 is 1/4, then look what happens. That's 15/16 and then 0. Because 1/4 squared, right? That's the y, square it. You get 1/16. 1 minus 1/16 is 15/16. So we are getting all these values. So let me plot these and see. Now, since we are dealing with such a small numbers, I'm going to say that the 4 units are number 1, right? Value. So this is my y-axis, this is my x-axis, and at 0 I am picking a vector, and we see that at 0, 0 vector is 1 unit long because this is where my number 1 is. And then I said 0, 1/2, which is here, and I got that the vector is something is wrong over here. I don't like it. So I have 1/4. 1 minus 1/4 is 3/4. Yeah. Looks like this. So that's when it's at half. This is when it's at 0. Now, 1/4 is right here. And then I get 15/16. It's right there. What's happening at 0 and 3/4? 0 and 3/4 is going to give me 9/16. So is that's 7/16, right? That's good, 7/16. Because 16 minus 9 is 7. Good. So at 3/4, I have just under the half. Right there. And what's happening at the boundary 0, 1? What's happening there? Very good. Vector is 0. The other side is going to be symmetric because it was 1 minus y squared. So we can just copy all of the values. Do you see what is happening here? What is this? It's flow. It's a flow. And this is how you describe flow. Through, well, this is two-dimensional flow, but you know that the liquid is moving faster in the middle than on the sides, because on the sides it experiences friction because it's hitting the walls. So this is the way to describe mathematically a flow, and then you can add the third dimension, right? And you can talk about the flow through a vessel. Flow of blood, flow of gasoline or kerosene, right, for fuel. So there's a lot of stuff that you can understand flow that is flow related. Now, what kind of flow we can think about? A flow of traffic, right? That could be something to consider, because that happens on the 2D surface. So flow of traffic is not really a three-dimensional problem. It's actually a 2D problem. Talking about cars. So that's that. One more. Let's try this one. So this one is negative xy, sorry, negative yx. There we go. So now, trying at 0, 0 clearly is just a 0, 0. So it's a 0 vector. We get nothing there. I think I'm going to go with 2 units in this case. All right, so let's see what's happening at 1, 0. So that's this point here, 1, 0. So vector f, 1, 0. So we plug in 0 for y and 1 for x, and I get 0, 1. That's this guy. What's happening at 0.01? Well, x is 0, so that's the second, and this is negative 1. So it points to the left. What is happening at negative 1, 0? Y 0, so that's 0. And then negative 1. That's this. And then we have at 0, negative 1. Is, so y is negative 1. We get 1, 0. What do we get here? Rotation. This is a counterclockwise rotation. And now, you can pick any point. It is not, this is not exclusive to these 4 points. You can pick any point you want on the on the graph here, let's pick negative 2, 2. Sorry, 2, negative 2. 2, negative 2. You can pick anything. So vector field at 2, negative 2, we have first coordinate is negative y, that's going to be 2, and the second is x, as is. It's a vector 2, 2. Now, how do we draw a vector 2, 2? Vector 2, 2 is going to be 2 units in x and 2 units in y. So 2 units in x, 2 units in y. This is how it looks like. Now that means that at 2, 2, there has to be another vector that does the same thing. 2 units up, 2 units over. So right here, it's going to look like this. You see that all of these vectors are turning stuff counterclockwise. Any vector that you draw on this plane will always tend to move everything this way, no matter where you put the vector. So we can talk about rotation, about shear, about flow, and then there is also radiation. We can get vectors that would radiate stuff out. You know that the sun in 3D, right, radiates around. So now I can talk about radial vector field, which would think of it as a source in the middle, and then just radiates out. Now, it's not only these 8 directions that I picked conveniently, everything in between. You can have anywhere else, right? There's going to be a vector here, and a vector here, and a vector here, and a vector here. They're everywhere. Just for convenience, we show a few of them. So these are important ones. They show up frequently. So the vector field for the radial field is given as xy divided by r to the p. And r is some scalar valued function. You know that energy is lost with distance. So depending on r and the p, the vectors that are further away become shorter, become weaker, right? The gravity falls off with the square of distance. Electric field, magnetic field, all of the fields in nature get weaker with distance. And you capture that with this part here. It doesn't have to be the square of the distance. It turned out that for gravity, magnetic field, and is square of the distance. So you always have distance squared. If you paid attention in your physics classes, you've constantly seen, like, to compute the force, the gravitational force, there was g m1 m2 divided by the distance squared, right? And then for the force, the electric field, you had the same thing. Charge 1, charge 2, divided by distance squared again, right? So all of these have the same equation all the time because it's fields, and they all behave the same way. In nature, they manifest differently, but the fabric that creates is the same. And that's why they have the same equation. We just use different constants. All right. Is there anything else that we should? And now the 3D case. So the vector field in 3D, we keep the same definition. I'm just going to write that this is x, y, z. And then we have the vector f, x, y, z, j, x, y, z, and age, x, y, z. And then if you're not lazy, you will write also the I, j, k. Now, obviously, these ones will be far more annoying to draw because you pick a 0, 0, 0, you pick 1, 0, 0, 1, 1, 0, 1, 1, 1, whatever, and you try to picture how they behave and what they do. Generally, I'll just show what the textbook shows. This stuff is cool, obviously, to show in Mathematica, which you could look up how to draw. But there is the cylinder flow, the one that I mentioned earlier, and it's going to have pretty much the same equation as before. You see that 1 minus x squared minus y squared. We used to have 1 minus y squared. That was it. And now you have this parabolic, right? Parabolic motion through the tube. So this is exactly what you use to describe the flow. Whether it's water, whether it's blood, whether it's fuel, doesn't matter what it is. It goes that way. One day, when you needed to have that drink with a straw, you don't have it. Because that's, yeah, there it is, a straw right there.
Like a crazy straw?
Relax. Regular straw, just a little bit thicker. Every time you take a sip, you feel like you're drowning. Right? I'm not really sure why are they going into this in here, because the part that I will just briefly mention now is actually 14.3, but I will mention it. So you note over here that these are functions of x, y, and z. Now remember when you do the gradient of f, what you get? Don't you get this? Right? The definition of the gradient is the vector of partial derivatives. Gradient is the one that creates fields, actually. You can generate a field by applying gradient to the function. Now, what 14.3 does is gives you the vector field, and if it's conservative and blah, 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 we'll see. There is a procedure to find the function, which we call potential function, which generates that field. And that is 14.3 calculation. Those problems are interesting. So right now, I'm just you know, making this parallel that you can generate vector field by just hitting the function with the gradient, and then you can take a look what you get. Now this will be on this side. This is a vector field now, and the function which generated that field is called a potential function.
So partial f partial x is the same thing as the f function in your array function.
No. You can have vector fields that do not have a potential function associated with them, which is exactly what breaks what you just asked. So this is just one way of creating a vector field. You take a function and you do the gradient. So every gradient is a vector field. But not every vector field has the potential function whose gradient would give it. Just like you can differentiate anything, but you can't integrate everything. Certain integrals do not have functions that you can differentiate to get them. So certain problems cannot be integrated, so in that sense. But we'll see more of that in 14.3, which is on the menu tomorrow. So the cool thing for tonight is just to play a little bit with these values, right? You have some vector field and you try to just get a sense of how to draw. Most of the exam questions are from 14.1 are either draw a 2D or a match the picture with the equation that it's given. But this is now opening that most important part of you guys figuring out the field so you can do mechanical, electrical, and other engineering, right? Because the field is the central idea of everything. And you guys are doing the extra problems for Maxwell's equations. I hope you read up on these things already and are familiar. So we'll talk more. So tomorrow, 14.2, line integrals. That's the first order of business. And then 14.3, conservative vector fields and potential function calculations. So see you tomorrow.